Hey guys, tonight we're going to explore something that sounds almost too abstract to matter. Time. Not the kind you check on your phone, not the hours that slip past during a commute, or the years that somehow vanished between school and now. We're talking about cosmic time, the kind of time that turns mountains into dust, the kind that watches galaxies form like raindrops and lets stars burn for billions of years before they even begin to fade. You think you understand how old things are. You know the pyramids are ancient. You know dinosaurs lived millions of years ago. You know the universe is roughly 13.8 billion years old. But here's what most people never truly grasp. The distance between those numbers isn't just big. It's so incomprehensibly vast that your brain will quietly give up trying to hold it all at once. And when you really sit with that scale, when you let yourself drift through the epochs and eras that stretch from the Big Bang to this exact moment, it changes how you see your own life entirely. By the end of this journey, you'll understand what it actually means to exist at the very edge of all that time, and how recent, how fragile, and how utterly strange your presence here really is. Before we go any further, if you find this kind of calm exploration valuable, a like or subscribe genuinely helps the channel grow. It's a small thing for you, but it makes a real difference for me, but only if you actually enjoy this. Now, dim the lights. Turn on a fan if that helps. Get comfortable, and let's begin. Let's start with something you already know. You woke up this morning. Maybe you checked the time. Maybe you thought about what day it is. Your brain keeps track of schedules, appointments, weekends. You measure your life in hours, days, years. You think of 10 years as a long time. 100 years feels like ancient history. But what if I told you that the entire span of recorded human history, everything from the first cities to the internet, is less than a single breath in the life of the universe? What if the dinosaurs, who ruled Earth for 165 million years, existed closer to us in time than they did to the formation of the Earth itself? What if the stars you see at night are already gone, and you're just watching their light arrive late, like a letter from the dead? Have you ever wondered what it would feel like to watch a billion years pass? Not in fast forward, not in a documentary, but to exist somehow outside time's current, observing as continents drift, species rise and vanish, stars ignite and collapse, all while you remain still. Would you feel awe, or would you feel something closer to vertigo? And slowly, you realize this isn't your usual evening. The rhythm of thought has changed. The sense of scale has shifted. You are now drifting backward through time itself, not as a traveler with a destination, but as a quiet observer, moving through the epochs like dust through a sunbeam, witnessing the universe as it unfolds in reverse, slowly, patiently, and with a kind of silence that makes even your heartbeat feel loud. The last ice age ended roughly 12,000 years ago. Glaciers that covered entire continents melted. Sea levels rose. Humans were already here, painting on cave walls and hunting mammoths. 12,000 years sounds ancient, but in cosmic terms, it's a blink. If Earth's entire history were compressed into a single year, the Ice Age ended about 3 seconds ago. You stand at the edge of a world transitioning from frozen to fertile. The air is cold but warming. You can feel it in the way the wind has changed, softer now, carrying moisture instead of the bone-dry chill of endless winter. Around you, ice sheets tower like mountains made of compressed snow and time. They've been here for 100,000 years, advancing and retreating in slow cycles dictated by the tilt of Earth's axis and the wobble of its orbit. But now, they're melting. It's not dramatic. There's no sudden crack, no Hollywood collapse, just a steady drip, a trickle that becomes a stream that becomes a river. Day after day, year after year, century after century, the ice surrenders to the sun. The water flows into valleys that haven't seen liquid in millennia. It pools in depressions, forming lakes that will one day become the Great Lakes, the Baltic Sea, thousands of smaller bodies of water that will define coastlines and civilizations. You watch the land emerge from beneath the ice like a secret being revealed. The ground is raw, scraped clean by glaciers that moved like slow-motion bulldozers. There are no trees yet, no grass, just rock, gravel, and mud. But life is coming. Seeds, frozen for thousands of years, begin to sprout. Mosses appear first, then shrubs, then trees, birch and pine, tough species that can handle the cold. Animals follow the plants. Reindeer, elk, bison, and behind them, humans. These humans aren't like you. They don't have cities or farms or written language, but they have tools, fire, and an understanding of the seasons that you, with your phone calendar, have mostly forgotten. They follow the herds. They know which plants are edible and which will kill you. They paint on cave walls, not as decoration, but as a way to communicate across time, a message to future hunters, or perhaps to the gods they believe control the weather. You realize something strange. These people are not that far removed from you. If you go back 12,000 years, you're only going back about 480 generations. Your great-great-great-grandmother, repeated 480 times, was alive during this. She had the same brain you have, the same capacity for love, fear, boredom, curiosity. She looked at the night sky and wondered what the lights were. She told stories to her children. She laughed at things that were funny and mourned people she lost. But her daily life was unimaginably harder than yours. She woke without an alarm because the sun did that job. She had no coffee, no breakfast waiting in the fridge. If she wanted to eat, she had to find food, which meant walking for miles, digging roots, tracking animals, or hoping the fish were biting. She wore animal skins because that's all there was. She had no mirror, so she never saw her own face clearly. She had no concept of germs, but she knew infection could kill, so she avoided deep cuts and treated wounds with whatever seemed to help: moss, clay, hope. She had no books, but she had memory. Everything important: how to make fire, where the safe plants grew, which stars meant winter was coming, was stored in her mind and passed down through speech. If she forgot, people could die. Memory wasn't just useful, it was survival. And here's the thing that makes this moment in time so strange. She was living at the threshold of everything. She didn't know it, but the Ice Age ending meant the world was about to change faster than it had in 100,000 years. The climate was stabilizing, temperatures were warming. In a few thousand years, her descendants would stop wandering and start planting seeds. They'd build permanent homes. They'd domesticate animals. They'd invent pottery, weaving, writing. They'd create cities, kingdoms, empires. But right now, in this moment, none of that exists. There's just ice melting, land emerging, and humans trying to survive one more day in a world that is slowly, imperceptibly, becoming the world you know. It's a bit like waiting for a software update to finish installing, except the progress bar is measured in millennia, and you don't even know an update is happening. You stand there, watching the glaciers retreat, and you realize this is the beginning of your story. Not the beginning of time, not even the beginning of life, but the beginning of the chapter that leads eventually, to you. And slowly, we drift further back. The first cities appeared around 4000 BCE. Writing, agriculture, kingdoms, everything we think of as human civilization is roughly 6,000 years old. That's 230 human generations. It sounds like a lot until you realize that sharks have been around for 450 million years. Civilization, by comparison, is a weekend experiment. You find yourself standing in southern Mesopotamia, in the land between the Tigris and Euphrates rivers. The air is hot, dry, thick with dust. The sky is a pale, washed-out blue, the kind of sky that makes you squint even in the shade. Around you, the world's first city is taking shape. It's not what you'd call a city by modern standards. There are no skyscrapers, no paved roads, no traffic lights. Just mud brick buildings clustered together, some single story, some two, with flat roofs where people sleep when the heat inside becomes unbearable. The streets are narrow, winding, more like footpaths that happen to become permanent. There's no central planning here. The city grew organically, one building at a time, as more people decided that living together was safer and more efficient than living alone. You watch as farmers return from the fields, carrying baskets of barley and wheat. This is new. For most of human history, people didn't farm. They hunted and gathered, moving with the seasons, following animal herds and ripening plants. But around 10,000 BCE, something shifted. People in this region started planting seeds on purpose. They noticed that if you put a seed in the ground and waited, food appeared. It sounds obvious now, but it was revolutionary then. Farming meant you could stay in one place. Staying in one place meant you could build permanent homes. Permanent homes meant you could accumulate possessions, pottery, tools, grain stores. Grain stores meant you needed someone to guard them. Guarding them meant you needed laws, leaders, soldiers. And suddenly, without anyone quite planning it, you had civilization. But civilization comes with trade-offs. The hunter-gatherers who lived here a few thousand years earlier worked fewer hours than these farmers. They had more varied diets. They didn't suffer from the crowd diseases, smallpox, measles, typhus, that come from living in close quarters with animals and each other. They didn't have kings taxing them or priests demanding offerings. But they also didn't have cities. They didn't have written language. They didn't have the ability to store knowledge outside of human memory. They couldn't build temples or monuments that would last thousands of years. They couldn't create art on a scale that would make future generations stop and stare. These farmers, on the other hand, are building something that will outlast them. They don't know it yet, but their city will become Uruk, one of the first true urban centers in human history. In a few hundred years, it will have a population of 50,000 people, unimaginable density for the time. It will have massive temples, complex irrigation systems, and scribes who record transactions on clay tablets, inventing writing in the process. You watch one of those scribes now, sitting in the shade, pressing a reed stylus into soft clay. He's not writing poetry. He's not recording history. He's counting grain. 12 bushels delivered to the temple, 3 bushels paid to workers. This is what writing was invented for: accounting. The first written words weren't love letters or prayers, they were receipts. It's a bit like realizing the internet was invented for military communication, and cat videos came later. The profound uses arrive after the mundane ones. You walk through the city, and you notice the smells: bread baking in clay ovens, smoke from cooking fires, human waste. Because there's no sewage system, people just throw it into the street or into designated pits outside the city walls. Animals everywhere, goats, sheep, chickens, all penned or wandering semi-freely. The noise is constant. Conversations, arguments, children playing, merchants shouting, hammers striking metal, wooden wheels creaking over dirt paths. This is humanity at a new density. For the first time, you don't know everyone around you. There are strangers here, people from other villages, other regions, speaking slightly different dialects. Trade has brought them. They come with goods: obsidian from the mountains, fish from the coast, copper from distant mines. The city is a hub, a crossroads, a place where different threads of human experience weave together. But it's also fragile. The whole system depends on the rivers. If they flood too much, the crops drown. If they don't flood enough, the crops wither. The irrigation canals need constant maintenance. Silt builds up. Channels get blocked. It takes coordinated labor to keep the water flowing where it needs to go. That's why there are leaders, administrators, overseers. Civilization requires organization on a scale that didn't exist before, and it requires something else: belief. You see the temple rising at the center of the city, a ziggurat made of mud bricks, step by step, reaching toward the sky. It's not finished yet. It won't be finished for years. But when it is, it will be the tallest structure these people have ever seen. It will be a place where priests commune with gods, where offerings are made, where the cosmic order is maintained. The people here believe the gods control the rivers, the weather, the fertility of the soil. They believe that if they don't make the right offerings, disaster will follow. And they're not entirely wrong. Disaster does follow regularly. Droughts, floods, plagues, invasions. The difference is, they interpret these events as divine punishment, while you might interpret them as bad luck or climate variability. But the outcome is the same. Civilizations rise and civilizations fall. This city, Uruk, will thrive for thousands of years. But eventually, the rivers will shift. The soil will become too salty from irrigation. Trade routes will change. Invaders will come, and the city will be abandoned, buried under sand, forgotten until archaeologists dig it up in the 20th century and realize this is where it all started. You stand in the heat and dust, watching people build the foundations of everything you take for granted: cities, laws, writing, trade, art, religion, and you realize how recent this all is. 6,000 years sounds like a long time, but it's not. It's 230 generations. If you lined up your ancestors, one for each generation, and walked past them shaking hands, you'd reach the beginning of civilization before lunchtime. And yet, everything you know, your language, your culture, your technology, your entire way of life, came from this fragile, ambitious experiment in living together. Slowly, we drift further back still. The Great Pyramid of Giza was built around 2500 BCE, roughly 4,500 years ago. Cleopatra lived closer to the invention of the iPhone than to the construction of the pyramids. And yet both of those events are infinitely closer to you than to the extinction of the dinosaurs, which happened 66 million years ago. Your brain wants to lump old things together, but the distances between them are staggering. You're standing in the desert west of the Nile, and the pyramids are being built. Not in the romantic, mysterious way you see in documentaries, in the hot, dusty, logistically complicated way that massive construction projects actually happen. There are thousands of workers here, not slaves, as popular myth suggests, but paid laborers, farmers working during the off-season when the Nile floods their fields. They're organized into teams with names like Friends of Khufu and Drunkards of Menkaure, a bit of dark humor to get through the brutal work. You watch as they drag a limestone block weighing 2.5 tons up a ramp. They use wooden sledges, ropes, and muscle. Someone pours water on the sand ahead of the sledge to reduce friction, a trick that actually works, as modern experiments have confirmed. The block moves slowly, inch by inch, accompanied by rhythmic chanting that helps coordinate the effort. It's going to take 20 years to finish this pyramid. 20 years of labor, planning, quarrying, transporting, placing over 2 million blocks of stone, each weighing an average of 2.5 tons. The precision is absurd. The base of the pyramid is level to within a few centimeters across a footprint of 13 acres. The sides are aligned almost perfectly with the cardinal directions. This is not primitive work. This is engineering on a scale that wouldn't be matched for thousands of years. But here's what's strange. Even to the people building it, ancient Egypt is already ancient. By the time Cleopatra was born in 69 BCE, the pyramids were already 2,400 years old. She lived closer to the moon landing than to the construction of these monuments. To her, the pyramids were tourist attractions, relics of a distant past, just as they are to you. The Egypt she ruled was a Hellenistic kingdom, Greek-influenced, cosmopolitan, more closely connected to Rome and Athens than to the old kingdom that built these tombs. And yet, when you think ancient Egypt, you probably think of pyramids, mummies, pharaohs with striped headdresses. You compress 3,000 years of history into a single aesthetic. It's like someone in the distant future thinking of ancient America and imagining George Washington, cowboys, and iPhones all existing at the same time. Time is deep, even in human history, and it gets deeper the further back you go. You walk away from the construction site and let your mind drift backward. 4,000 years, 40,000 years, 400,000 years. The pyramids vanish. The cities vanish. Humans are still here, but they're different. Archaic Homo sapiens, then Homo heidelbergensis, then Homo erectus. You keep going back, and the hominids become more ape-like until you reach a common ancestor with chimpanzees about 6 million years ago. 6 million years is a long time, but it's nothing compared to what's coming. You keep drifting. 10 million years, 20 million, 50 million. The continents are in different positions. India is still an island, slowly crashing into Asia, pushing up the Himalayas. The climate is warmer. There are forests where there are now deserts. Strange mammals roam the earth. Early whales that still have legs, giant flightless birds that are the apex predators in some regions. You go back further, 66 million years, and suddenly you hit a boundary. This is the moment the dinosaurs died. An asteroid 6 miles wide slammed into the Yucatan Peninsula with the force of 1 billion atomic bombs. The impact vaporized rock sent a plume of superheated debris into the atmosphere and triggered earthquakes, tsunamis, and wildfires across the globe. Within hours, the sky was dark. Within days, the temperature dropped. Within months, most of the large animals were dead. It wasn't immediate for everyone. Some dinosaurs survived the impact itself, but the sun was blocked by dust and soot. Plants died. Herbivores starved. Carnivores had nothing to hunt. The food chain collapsed from the bottom up. 75% of all species went extinct. But here's the thing. The asteroid didn't kill everything. Small mammals survived. Birds, descendants of dinosaurs, survived. Crocodiles, turtles, some fish, some insects. Life persisted. And in the aftermath, in the emptiness left behind, the survivors radiated into new forms. Mammals, which had been small and nocturnal for over 100 million years, suddenly had space to grow. Within 10 million years, there were mammalian predators, herbivores, climbers, swimmers. Within 20 million years, there were whales, bats, primates. The world restructured itself entirely. And all of this, the asteroid, the extinction, the rise of mammals, the eventual appearance of humans, the construction of the pyramids, and your life right now. All of this is infinitely closer to the present than to the beginning of the dinosaurs' reign. Because the dinosaurs didn't just exist for a few million years, they dominated Earth for 165 million years. To put that in perspective, the time between the Stegosaurus and the Tyrannosaurus rex is greater than the time between T-Rex and you. When T-Rex was alive, Stegosaurus fossils already existed. Deep time is so deep that even within the age of dinosaurs, there are epochs as distant from each other as ancient Egypt is from you. Your brain doesn't want to accept this. It wants to compress the past into something manageable. But the past is not manageable. It's vast, inhuman, and utterly indifferent to your sense of scale. You stand in the desert, watching workers haul stones, and you realize this pyramid, this monument meant to last forever, is a brief flicker in the timeline of life on Earth. And life on Earth is a brief flicker in the timeline of the planet. And the planet is a brief flicker in the timeline of the universe. And slowly we drift further back. Dinosaurs existed from roughly 230 million years ago to 66 million years ago. That's 165 million years of dominance. Humans, in our current form, have existed for about 300,000 years. If the age of dinosaurs were a 24-hour day, humans would have appeared in the last 4 seconds. We are cosmically, embarrassingly new. You're standing in a forest, but it's not a forest you'd recognize. The trees are familiar in shape but wrong in detail. There are conifers, cycads, ferns the size of houses, but no flowers, no grass, no oak, maple, or birch. Those haven't evolved yet. The air is thick, humid, oxygen-rich. It smells green, like a greenhouse that's been sealed for 1,000 years. And then you hear it. A low rumble. Not quite a growl, not quite a groan. Something between a bass drum and distant thunder. The ground trembles slightly. Birds. Small, feathered. Definitely birds, even though they look a bit too reptilian. Scatter from the trees. You turn, and there it is. A dinosaur. Not a skeleton in a museum. Not a CGI effect. A living, breathing, moving creature the size of a bus. It's an apatosaurus, or something like it. A long-necked sauropod moving slowly through the forest, its head high in the canopy, stripping leaves from branches with a methodical, cow-like indifference. It doesn't notice you. You're too small, too irrelevant. It's focused on eating, which is what it does most of the day, because when you weigh 30 tons, you need a lot of calories. You watch it move, and you're struck by how normal it seems. Not monstrous, not alien, just an animal. It has behaviors, needs, instincts. It's careful where it steps. It pauses to scratch itself against a tree. It makes soft vocalizations, contact calls maybe, to others of its species nearby. This is not a monster. This is a herbivore trying to get through the day without being eaten, because there are things here that want to eat it. You hear a different sound now, a sharp, high-pitched call. Then another, answering. You freeze. Somewhere in the underbrush, something is moving. Something smaller, faster, and very interested in whether you're edible. A pair of velociraptors emerge from the ferns. They're not as big as Jurassic Park suggested, about the size of turkeys covered in feathers, with sickle-shaped claws on their hind feet. But they're focused, intelligent, coordinated. They hunt in packs, and they're looking at you the way a cat looks at a bird. You back away slowly, and they lose interest. You're too big, too strange. They turn and disappear into the forest, probably tracking something smaller. You exhale. This is the Cretaceous period, roughly 75 million years ago. Dinosaurs have been the dominant land animals for over 150 million years at this point. They've evolved into thousands of species, filling every ecological niche. Herbivores, carnivores, scavengers, insectivores. Some are enormous, some are tiny, some have armor, horns, frills, crests. Some have feathers and will eventually become birds. They are not a failed experiment. They are not evolutionary dead ends. They are one of the most successful groups of animals ever to exist on Earth. And they will be gone in a geological instant. But right now, in this moment, they own the world. You walk through the forest, carefully, and you notice the details. Insects everywhere, dragonflies the size of your hand, beetles with iridescent shells, ants that look almost modern. Flowers have recently appeared, a new invention, and with them, bees. The coevolution of plants and pollinators is just beginning. There are mammals here too, small ones, shrew-like creatures that scurry through the underbrush, nocturnal, cautious, always one step away from being someone's snack. They're not impressive. They've been around almost as long as the dinosaurs, but they've stayed small. There's no room to grow when the dinosaurs occupy every large animal niche, but they're patient. Evolution is patient. You sit on a fallen log, carefully, because even the insects here might be dangerous, and you think about time. Humans have existed in our current form for about 300,000 years. That sounds like a lot. It feels ancient, but compared to the dinosaurs, it's nothing. If you compressed the age of dinosaurs into a single 24-hour day, humans would appear in the last 4 seconds. All of recorded history, every civilization, every war, every work of art would fit into the last 1/10 of a second. We are so new that we barely register, and yet we act like we own the planet. We reshape landscapes, alter the climate, drive species to extinction. We've been here for a geological eye blink, and we're already leaving a mark that will be visible in the rock record millions of years from now. The dinosaurs, for all their size and dominance, didn't do that. They lived within the ecosystem. They evolved with it. They didn't build cities or invent agriculture or create plastic. They were just animals, very successful animals, but animals nonetheless. You watch the Apatosaurus in the distance, still eating, still indifferent, and you feel a strange mixture of awe and sadness, because you know what's coming. In a few million years, an asteroid will fall from the sky, and this entire world will end, not slowly, not gracefully, but in fire and darkness and a long, cold winter that will kill almost everything, and the small, patient mammals hiding in burrows will inherit the earth. It's a bit like watching a company dominate the market for over a century, only to be destroyed overnight by a technology they never saw coming. Except the technology is a 6-mile-wide rock traveling at 45,000 miles per hour. You stand up, brush off the dirt, and let time carry you backward once more. 66 million years ago, a 6-mile-wide asteroid slammed into what is now the Yucatan Peninsula. The impact released the energy of roughly 1 billion atomic bombs. 75% of all species went extinct. The world burned, then froze, then slowly reassembled itself into something unrecognizable. This is the reset button that allowed mammals, and eventually you, to exist. You're floating above the Earth 66 million years ago, watching. The planet below looks different. The continents are in the wrong places. North and South America are separated by a seaway. India is an island. Antarctica is green and forested. The climate is warmer than it will be in your time. There are no ice caps. And then, without warning, the sky lights up. A streak of light appears, growing brighter, faster, impossibly fast. It's an asteroid, 6 miles across, composed of rock and metal, traveling at 45,000 miles per hour. It has been falling toward Earth for millions of years, pulled by gravity, silent and inevitable. It strikes the Yucatan Peninsula. The impact is beyond anything you can comprehend. The asteroid punches through the atmosphere in less than a second. It hits the shallow sea with the force of 1 billion nuclear bombs detonating simultaneously. The rock vaporizes instantly. So does a chunk of the Earth's crust. A fireball expands outward, reaching temperatures hotter than the surface of the sun. A shockwave radiates from the impact site, flattening forests, triggering earthquakes that register magnitude 10 or higher. Tsunamis hundreds of feet tall race across the ocean, scouring coastlines clean. The impact ejects trillions of tons of debris into the atmosphere: molten rock, vaporized minerals, pulverized limestone that releases carbon dioxide and sulfur. Some of this debris reaches escape velocity and is flung into space. Some of it falls back to Earth as a rain of molten glass, igniting wildfires across entire continents. Within hours, the planet is burning. You watch from your impossible vantage point as the sky turns red, then black. The sun disappears behind a curtain of ash and soot. The temperature spikes briefly from the heat of the impact and the global firestorms, then plummets as the sun is blocked. Photosynthesis stops. Plants begin to die. In the ocean, phytoplankton, the base of the marine food web, dies. Without phytoplankton, the small fish die. Without small fish, the larger fish die. The food chain collapses. On land, herbivorous dinosaurs run out of food within weeks. Carnivorous dinosaurs with nothing to hunt starve soon after. Some animals survive longer. Scavengers, opportunists, anything that can eat the dead. But the dead run out eventually. The impact winter lasts for years, maybe decades. The sky remains dark. The temperature stays low. Acid rain falls, poisoning rivers and lakes. The soil becomes toxic. 75% of all species go extinct. But not everything dies. Some animals survive. Small mammals that can burrow underground and hibernate. Birds that can migrate or adapt their diets. Crocodiles and turtles, which can go months without food. Insects, which reproduce quickly and can survive on almost anything. Deep-sea creatures, insulated from the worst of the surface chaos. Life doesn't end, but it's reset. The dominant players are removed. The niches they occupied are suddenly empty. And in the aftermath, in the slow recovery, the survivors begin to evolve into new forms. You watch as the sky gradually clears. Decades pass, centuries. The sun returns, weak at first, then stronger. Plants begin to grow again, first ferns, which are hardy and fast-growing, then other species. The forests return, though they're different now. New species, new dynamics. And the mammals, which have been small and nocturnal for over 100 million years, begin to grow. Without dinosaurs to compete with, they radiate into new ecological niches. Some become herbivores, eating the returning plants. Some become carnivores, hunting the herbivores. Some take to the trees. Some take to the water. Within 10 million years, the world is unrecognizable. There are mammalian predators the size of bears. There are herbivores experimenting with different body plans, some developing hooves, some developing trunks, some growing to enormous sizes. Evolution is filling the empty spaces left by the dinosaurs. And eventually, tens of millions of years later, one lineage of small tree-dwelling mammals will develop grasping hands, forward-facing eyes, and complex social behaviors. They will become primates. And from them, eventually, will come you. You exist because an asteroid fell from the sky 66 million years ago and killed almost everything. It's a sobering thought. Your entire existence is contingent on a cosmic accident. If the asteroid had been slightly smaller, or struck at a different angle, or missed Earth entirely, dinosaurs might still be here. Mammals might still be small, nocturnal, and irrelevant. There would be no humans, no cities, no art, science, or philosophy. No one to look up at the stars and wonder where we came from. The universe doesn't care about fairness or destiny. It just happens. Rocks fall, species die, new species emerge. Time moves forward, indifferent and patient. You float above the earth, watching the recovery, and you realize this is not the first time life has nearly ended, and it won't be the last. But for now, life persists. It adapts. It fills the empty spaces. It becomes more complex, more diverse, more resilient, and slowly we drift further back. Mammals first appeared around 200 million years ago, small and nocturnal, scurrying beneath the feet of dinosaurs. They stayed small for over 130 million years. Patience, in evolutionary terms, is waiting for an asteroid to give you a chance. Eventually, it did. You're in the Triassic period now, roughly 210 million years ago, and the world is still recovering from the worst mass extinction in Earth's history. 90% of all species died in the Permian-Triassic extinction event about 252 million years ago. It was worse than the asteroid that killed the dinosaurs. It was worse than anything before or since. Volcanic eruptions in Siberia released so much carbon dioxide and sulfur that the oceans became acidic and oxygen depleted. The temperature spiked. Life nearly ended. But it didn't. And now, in the aftermath, new forms are emerging. You're standing in a forest at twilight. The air is warm, humid. The plants are strange, mostly ferns and conifers with some early seed plants. There are no flowers yet. The landscape has a prehistoric alien quality, like a place that hasn't decided what it wants to be yet. You hear something moving in the underbrush, something small. You crouch down and watch as a tiny creature emerges. It's about the size of a mouse, covered in fur, or something like fur, proto-fur, the evolutionary precursor to what mammals will have later. It has a long snout, tiny eyes, and whiskers. It moves cautiously, sniffing the air, alert to danger. This is one of the first mammals. It doesn't look like much. It's not impressive. It won't grow into anything impressive for over 100 million years. But it has something the reptiles around it don't have. It's warm-blooded. It can regulate its own body temperature, which means it can be active at night when the cold-blooded dinosaurs are sluggish. This is its niche, the night shift. During the day, dinosaurs rule. They're bigger, faster, more powerful. But at night, when the temperature drops and the reptiles slow down, the mammals come out. They hunt insects, eat seeds, scavenge. They stay small, stay quiet, stay out of sight. For 130 million years, this will be their strategy. Survive. Don't compete directly. Wait for an opportunity. It's a bit like being a startup in a market dominated by giants. You don't try to beat them head on. You find a niche they're ignoring, and you survive there until the market changes. You watch the tiny mammal as it catches an insect, chews quickly, and scurries back into the underbrush. It's unremarkable, but it's persistent. And persistence, in evolutionary terms, is everything. The dinosaurs will dominate for over 160 million years. They'll grow larger, more diverse, more specialized. They'll become the most successful land animals in Earth's history. But the mammals will wait. They'll stay small. They'll stay nocturnal. They'll develop better hearing, better smell, better temperature regulation. They'll evolve live birth instead of laying eggs, which gives their young a better chance of survival. They'll develop complex teeth that can process different types of food. They're building advantages slowly, quietly, without anyone noticing. And then, 66 million years from now, an asteroid will fall, and the dinosaurs will die. And the mammals, patient and adaptable, will inherit the Earth. But that's still unimaginably far in the future. Right now, in this moment, they're just small, furry creatures trying to survive one more night. You stand up and look around. The forest is full of sounds, chirping insects, distant calls of early dinosaurs, the rustle of wind through unfamiliar leaves. This world is still young, still experimental. Evolution is trying things out, seeing what works. Most of what's here will go extinct. Most lineages will dead end. But some will persist. Some will adapt. Some will become the ancestors of everything that follows. You take a breath of the thick, humid air, and you realize you're standing at the beginning of a lineage that will eventually include whales, bats, elephants, primates, and you. It all started here, with small, unimpressive creatures hiding from dinosaurs. And slowly, we drift further back. The first dinosaurs emerged around 230 million years ago during the Triassic period. The continents were fused into one massive landmass called Pangaea. There were no flowers, no grass. The air was thicker, hotter, and filled with creatures that looked like nightmares. This is deep time, so far back that even the landscape is alien. You're standing on Pangaea, the supercontinent, 230 million years ago. The ground beneath your feet is red sandstone, baked hard by relentless sun. The sky is a hazy, pale orange, thick with dust. There are no oceans nearby. You're in the interior of the continent, hundreds of miles from the coast, in a vast desert that stretches in every direction. The temperature is brutal, over 100 degrees Fahrenheit during the day. There's no shade, no trees, just low scrub, ferns in the gullies where water occasionally flows, and rocky outcrops sculpted by wind. This is not a hospitable place, but life is here. You see movement in the distance, something large, walking on 4 legs. It's not a dinosaur, not yet. It's a therapsid, a distant relative of mammals, a bulky, reptilian creature with sprawling limbs and a thick, armored hide. It's one of the survivors of the Permian extinction, clinging to existence in this harsh new world. And then you see something else. A smaller creature, moving quickly, bipedal, with a long tail for balance. It's lean, agile, built for speed. It has sharp teeth and alert eyes. It's hunting. This is one of the first dinosaurs. It's not impressive yet. It's about the size of a dog, opportunistic, competing with larger predators for scraps. But it has advantages. It's warm-blooded, or at least closer to warm-blooded than most reptiles. It can move efficiently. It can sustain activity longer than its cold-blooded competitors. Over the next several million years, this small advantage will compound. Dinosaurs will grow larger, more diverse, more dominant. They'll split into 2 major lineages: the Saurischians, lizard-hipped, and the Ornithischians, bird-hipped. From these, all future dinosaurs will descend: long-necked sauropods, armored ankylosaurs, horned ceratopsians, and eventually, birds. But right now, They're just scrappy little predators trying to survive in a brutal world. You watch the early dinosaur as it stalks a small reptile, pounces, and tears into it with sharp teeth. It eats quickly, alert for larger predators. Even here, at the beginning, the instinct is the same. Eat, don't get eaten, reproduce. The landscape around you is alien in ways that go beyond just the plants and animals. The very geography is wrong. All the continents are joined into one massive landmass, which means the interior is extremely dry. There's no ocean to moderate the temperature, no moisture carried inland by coastal winds. The center of Pangaea is a desert, and it will remain that way for millions of years. Eventually, Pangaea will begin to break apart. The Atlantic Ocean will open, the continents will drift, but that's still over 100 million years away. For now, the world is locked in this configuration, and life has to adapt to it. You walk across the red sandstone, feeling the heat radiate up through your feet, and you think about how alien this all is. Not just alien in the sense of unfamiliar, but alien in the sense that the rules seem different. The air is thicker, higher oxygen content. The sun feels harsher. The ozone layer is thinner. The days are shorter. Earth is spinning faster, so a day is only about 23 hours long. Even time itself feels different here. You find a rocky outcrop and sit in the shade it provides. You watch the early dinosaur disappear into the distance, and you realize this is the beginning of an era that will last 165 million years. The dinosaurs will rise from these humble beginnings to dominate the planet. They'll grow to sizes never seen before or since. They'll develop armor, horns, crests, wings. They'll spread across every continent. They'll survive multiple smaller extinction events. They'll be so successful that it will seem like they'll last forever. But they won't. Nothing lasts forever. And slowly, we drift further back. For billions of years, life on Earth was mostly single-celled and boring. Then, around 540 million years ago, something extraordinary happened. The Cambrian explosion. Suddenly, in a geological eye blink, complex organisms appeared. Animals with shells, eyes, limbs, predators, prey. Evolution hit the gas pedal, and nothing was ever slow again. You're underwater now, floating in a shallow sea 540 million years ago. The water is warm, clear, illuminated by sunlight filtering down from above. The ocean floor beneath you is covered in fine sediment, rippled by gentle currents. And everywhere you look, there is life, not the life you know, not fish or coral reefs or kelp forests. This is earlier, stranger. This is the Cambrian period, and you're witnessing one of the most dramatic transformations in the history of life on Earth. For 3 billion years before this moment, life was simple. Bacteria, algae, simple multicellular organisms that looked like blobs or mats or filaments. Nothing with eyes, nothing with a skeleton, nothing that could chase, fight, or defend itself in ways you'd recognize. But something changed. Maybe it was rising oxygen levels. Maybe it was a shift in ocean chemistry. Maybe it was an evolutionary arms race triggered by the first predators. Whatever the cause, life suddenly became complex. You watch as a creature scuttles across the seafloor. It's called Anomalocaris, and it's the apex predator of this time. It's about 3 feet long, with a circular mouth ringed with teeth, compound eyes on stalks, and swimming flaps along its sides. It looks like something designed by a committee that couldn't agree on what an animal should be, but it's effective. It's fast. It hunts. Nearby, a trilobite, one of the most successful animals of this era, crawls across the sediment. It has a hard exoskeleton divided into segments, jointed legs, and compound eyes. It's an arthropod, a distant relative of insects and crustaceans, trilobites will survive for nearly 300 million years, adapting to every marine environment before finally going extinct in the Permian extinction. But right now, they're brand new, and they're everywhere. You see other creatures too. Some have shells shaped like cones or spirals. Some have spines protruding in every direction, like underwater porcupines. Some burrow into the sediment. Some filter feed. Some are predators. Some are scavengers. There's an explosion of body plans, of evolutionary experiments. Some will succeed and give rise to entire lineages. Others will dead end, leaving only fossils and ancient rock layers, evidence of paths not taken. This is what paleontologists call the Cambrian explosion, and it's one of the great mysteries of biology. Why did it happen so suddenly? Why, after billions of years of simplicity, did life suddenly become complex? The answer is probably a combination of factors. Oxygen levels in the atmosphere and oceans had been rising, thanks to photosynthetic bacteria and algae. Higher oxygen meant larger, more active bodies were possible. Predation became a thing. Once one organism figured out how to eat another, everyone else had to evolve defenses. Hard shells, spines, speed, camouflage. An evolutionary arms race began, and once it started, it accelerated. It's a bit like the tech industry. For decades, progress is incremental. Then someone invents the internet, and suddenly everything changes at once. New companies, new products, new business models. Innovation breeds more innovation. That's what's happening here, in this shallow Cambrian sea. Evolution is innovating. You float above the sea floor, watching the trilobites and the Anomalocaris and the dozens of other strange creatures whose names you don't know. Most of these specific species will go extinct, but the innovations they represent, eyes, exoskeletons, jointed limbs, nervous systems, predator-prey dynamics, those will persist. These are the foundations of all future animal life. Every animal alive today, including you, can trace its lineage back to something that lived in this sea. You are descended from some small, worm-like creature that survived the Cambrian, adapted to changing conditions, and eventually gave rise to fish, then amphibians, then reptiles, then mammals, then primates, then humans. Your family tree goes back to this moment. You watch a small, eel-like creature called Pikaia swim past. It has a notochord, a flexible rod running along its back, a precursor to a backbone. It's not impressive. It's not the apex predator. It's not even particularly common. But it's your ancestor. That small, unassuming creature is part of the lineage that will eventually become all vertebrates. Fish, amphibians, reptiles, birds, mammals. Everything with a spine descends from something like Pikaia. You feel a strange connection to it. This little swimmer, navigating a dangerous world, just trying to survive, contains within its DNA the potential for everything you are. It doesn't know that, of course. It's just trying not to get eaten. But you know. You can see the line stretching forward from this moment, through mass extinctions and ice ages and continental shifts, through millions of generations of adaptation and mutation, leading eventually to you. It's humbling and a little absurd. You exist because this weird little protofish was good at not dying. And slowly, we drift further back. 2.4 billion years ago, cyanobacteria began producing oxygen as a waste product. It poisoned most of the planet's existing life. The atmosphere changed. Rust formed on rocks for the first time. This event, called the Great Oxidation Event, was an environmental catastrophe that eventually allowed you to breathe. You exist because of ancient bacteria pollution. You're floating above the Earth, 2.4 billion years ago, and the planet looks wrong. The sky is not blue. It's a pale, hazy orange-pink, thick with methane and carbon dioxide. There's no ozone layer yet, so ultraviolet radiation pours down unfiltered. The land is barren, lifeless rock, no plants, no animals, no soil, just stone, baked by the sun, weathered by wind and rain. But the oceans are alive. You descend into the water, and immediately you notice the color. The sea is tinged green with massive blooms of cyanobacteria, simple photosynthetic microbes that have been around for hundreds of millions of years. They float in vast mats, covering the surface, soaking up sunlight. And they're doing something that will change the world forever. They're producing oxygen. It's a waste product for them, a byproduct of photosynthesis. They take in carbon dioxide and water, use sunlight to break them apart, and release oxygen into the environment. They don't know they're doing it. They have no awareness, no intention. They're just following the chemical processes encoded in their biology. But the oxygen they produce is building up. For millions of years, the oxygen was absorbed by iron dissolved in the oceans. The iron rusted, turned red, and sank to the ocean floor, forming distinctive red layers in the rock that geologists call banded iron formations. These layers are some of the clearest evidence we have of the Great Oxidation Event. But eventually, the oceans ran out of dissolved iron, and the oxygen had nowhere to go except into the atmosphere. This was a catastrophe. Most of the life on Earth at this time was anaerobic. It lived in environments without oxygen. To these organisms, oxygen was toxic. It reacted with their cellular structures, damaged their DNA, killed them. The Great Oxidation Event was a mass extinction. Entire ecosystems collapsed. Species that had thrived for hundreds of millions of years were wiped out. But some organisms survived. Some adapted. Some already had mechanisms to deal with oxygen, or they evolved them quickly. Some learned to use oxygen for metabolism, which turned out to be incredibly efficient. Aerobic respiration produces far more energy than anaerobic processes, and over time, these oxygen-breathing organisms became the dominant forms of life. Without the Great Oxidation Event, you wouldn't exist. Complex, multicellular life requires oxygen. Your cells need it to produce energy. Your brain, your muscles, your every thought and movement depend on a steady supply of oxygen delivered by your blood. You exist because ancient bacteria polluted the atmosphere with a waste product that happened to be useful. It's a bit like if a factory dumped chemicals into a river for centuries, accidentally creating conditions that allowed a new ecosystem to thrive. Except in this case, the factory was microscopic, the chemicals were oxygen, and the new ecosystem was everything you see around you. You float in the ancient ocean, watching the cyanobacteria bloom, and you think about unintended consequences. These bacteria didn't mean to change the world. They didn't have a plan. They were just living, doing what their biology told them to do. And in the process, they transformed the planet so completely that nothing was ever the same. The atmosphere changed. The chemistry of the oceans changed. The types of minerals that formed on land changed. Rust appeared for the first time, iron oxides that stained rocks red. The sky slowly shifted from orange-pink to pale blue as oxygen accumulated. Life created the conditions for more complex life. It's a feedback loop. Organisms change their environment. The changed environment selects for new types of organisms. Those organisms change the environment further. The cycle continues. And eventually, billions of years later, you appear. A product of that long, slow process, dependent on the oxygen those ancient bacteria produced. You take a breath, even though you're imagining this, and you realize every breath you take connects you to this moment. The oxygen in your lungs was first produced by bacteria that have been dead for billions of years. You are breathing ancient waste, and slowly, we drift further back. Life on Earth likely began around 3.8 billion years ago. Not complex life, not even bacteria as you'd recognize them, just self-replicating molecules in shallow water, perhaps near hydrothermal vents, blindly experimenting with chemistry. This is the moment the universe began paying attention to itself, one molecule at a time. You're standing, or rather hovering, near the edge of a shallow pool, 3.8 billion years ago. The Earth is young, barely 700 million years old. It has only recently cooled enough for liquid water to exist on the surface. The oceans have formed. The atmosphere is thick with water vapor, carbon dioxide, methane, ammonia. The sky is dark, stormy, constantly flickering with lightning. The surface of the planet is being bombarded by asteroids and comets, leftovers from the formation of the solar system. Impacts happen regularly, some large enough to vaporize entire oceans. But the water comes back. Ice from comets replenishes it. The cycle continues. The pool in front of you is warm, heated by volcanic activity. It's shallow, maybe a few feet deep, located near a hydrothermal vent where mineral-rich water bubbles up from beneath the crust. The water is cloudy, full of dissolved chemicals, iron, sulfur, phosphates, organic molecules brought by meteorites or formed in the atmosphere and washed down by rain. And in this pool, something is happening. Molecules are bumping into each other, driven by heat and chance. Some stick together, some break apart. Most do nothing interesting. But some, a very few, do something extraordinary. They copy themselves, not perfectly, not with any kind of intention, but through random chemical processes. Some molecules act as templates, attracting other molecules that fit their shape, building copies. Most of these copies fall apart immediately, but some are stable. Some last long enough to make more copies. This is not life yet. Not really. There's no cell, no membrane, no metabolism, just chemistry that happens to be self-perpetuating. But it's the beginning. Over millions of years, these self-replicating molecules become more complex. They develop membranes, lipid bubbles that protect them from the environment. They develop metabolism, ways to harvest energy from their surroundings. They develop the ability to respond to stimuli, to move, to compete for resources. They become the first cells, simple, primitive, barely distinguishable from the chemistry around them, but alive. You watch the pool, knowing that somewhere in that cloudy water, the transition is happening. Non-life is becoming life. The universe, which has been unconscious for 13 billion years, is beginning to wake up, because that's what life is, in a sense. It's the universe becoming aware of itself. A rock doesn't know it exists. A star doesn't observe the planets around it. But life senses, responds, reacts. Even a simple bacterium detects light, moves toward nutrients, avoids toxins. It's rudimentary awareness, but it's awareness. And from this humble beginning, everything else follows. Over the next 3.8 billion years, life will evolve into millions of forms. It will colonize every environment on Earth: oceans, lakes, rivers, soil, ice, deep underground, high in the atmosphere. It will survive mass extinctions, asteroid impacts, ice ages, supervolcano eruptions. It will become more complex, more diverse, more resilient, and eventually, it will produce you. A creature made of trillions of cells, each one a descendant of that first simple cell in the warm pool. a creature with a brain capable of abstract thought, language, art, science. A creature that can look back across billions of years and understand, roughly, how it came to be. You exist because chemistry became biology, because molecules learned to copy themselves, because random processes, given enough time, can produce complexity. There's no plan here, no designer, just the patient, relentless working of natural laws across unimaginable spans of time. It's a bit like leaving a room full of Lego bricks and coming back a billion years later to find they've assembled themselves into a city. Except the Lego bricks are atoms, the city is life, and the assembly process is evolution. You watch the pool, steam rising from the surface, minerals precipitating out in strange colors, and you think about beginnings. This is where it started. Not with a bang, not with a divine proclamation, but with quiet chemistry in a warm, shallow pool. Life didn't arrive fully formed. It didn't appear suddenly. It emerged gradually, almost imperceptibly, from non-life. And once it started, it never stopped. And slowly, we drift further back. 4.5 billion years ago, a cloud of gas and dust orbiting a young star began to clump together. Gravity pulled it tighter. The clumps collided, melted, fused. Eventually, one of those clumps became Earth. You are standing on recycled stardust that took millions of years to cool enough to hold water. You're floating in space, watching the birth of a planet. The scene in front of you is chaos. There's a young star in the center, the sun, barely 1 million years old, still surrounded by a disk of gas and dust left over from its formation. The disk is thick, opaque, glowing faintly from the heat of collisions happening constantly within it. And within that disk, something is happening. Tiny grains of dust, smaller than sand, composed of silicates, metals, ices, are sticking together. Electrostatic forces hold them at first. Then gravity takes over. The grains become pebbles. Pebbles become rocks. Rocks become boulders. This process is called accretion, and it's happening everywhere in the disk. You watch as two boulder-sized objects collide. They don't bounce off each other. They're moving slowly enough, and their gravity is strong enough that they stick together. The combined mass is now larger, with stronger gravity, which attracts more material. Planetesimals form, objects miles across, irregular in shape, spinning slowly. And then the planetesimals start colliding with each other. These collisions are violent. When two planetesimals hit, they release enormous amounts of energy. Rock melts, material is ejected, but some of it stays, and the combined object grows larger. You watch as one particular planetesimal, over millions of years, grows larger than the others in its orbital zone. It's sweeping up everything nearby. It's becoming a planet. This is Earth, in its earliest form. It doesn't look like Earth yet. There are no oceans, no atmosphere, no continents. It's just a ball of molten rock, glowing red hot from the heat of constant impacts. The surface is a magma ocean, liquid rock miles deep, churning and convecting. The temperature is over 2,000 degrees Fahrenheit. Nothing solid can exist on the surface. Everything melts, and the bombardment continues. Asteroids and comets, leftovers from the formation of the solar system, rain down constantly. Some are small, burning up in the thin, early atmosphere. Some are large, slamming into the surface with the force of nuclear weapons, adding their mass to the growing planet. This goes on for tens of millions of years. Slowly, the bombardment decreases. The solar system is clearing out. Most of the loose material has either been incorporated into planets or ejected from the system. Earth begins to cool. The surface starts to solidify. A crust forms, thin, unstable, constantly broken apart by volcanic activity and impacts, but solid nonetheless. Water vapor in the atmosphere begins to condense. Rain falls for the first time, vaporizing as soon as it hits the hot surface, but gradually cooling the planet. Eventually, the surface is cool enough for liquid water to persist. The first oceans form. They're not like the oceans you know. They're hot, acidic, full of dissolved minerals. The atmosphere is thick with carbon dioxide and water vapor. There's no oxygen, no life, no sound except the crashing of waves and the rumble of volcanoes. But it's Earth. You float above this young planet, watching it take shape, and you think about what you're made of. Every atom in your body was forged in a star. The hydrogen in your water came from the Big Bang. The carbon in your cells, the oxygen in your lungs, the calcium in your bones, the iron in your blood. All of it was created in the cores of stars that exploded billions of years ago. Those stars fused lighter elements into heavier ones, building up the periodic table through nuclear reactions. When they ran out of fuel, they exploded in supernovae, scattering their enriched material across space. That material drifted through the galaxy, eventually collapsing into a new cloud of gas and dust. That cloud became the sun and the planets, and one of those planets became Earth, and Earth eventually became you. You are made of stardust, not metaphorically, literally. The atoms in your body are ancient, recycled from dead stars, reformed into planets, dissolved in oceans, incorporated into living cells, passed down through billions of generations. You are the universe experiencing itself. It's a cliché, but it's true. For 13.8 billion years, the universe has been doing chemistry and physics, atoms combining, stars forming, galaxies colliding, and somewhere along the way, on at least one planet orbiting an ordinary star, the chemistry became complex enough to produce life, and the life became complex enough to produce awareness, and the awareness became complex enough to look back and understand, roughly, how it all happened. You are the result of that process. You float above the early Earth, watching the oceans condense and the volcanoes erupt, and you realize this ball of molten rock will one day have forests, mountains, rivers, cities. It will be home to billions of organisms, each one struggling to survive, each one carrying the legacy of 4.5 billion years of planetary history. And somewhere, billions of years in the future, a member of a particularly curious species will look up at the night sky and wonder how it all began. And slowly, we drift further back. Shortly after Earth formed, a Mars-sized object called Theia smashed into it. The collision vaporized rock, sent debris into orbit, and eventually coalesced into the Moon. Without that violent accident, Earth's tilt would wobble chaotically, and life as you know it probably wouldn't exist. You owe your stability to an ancient disaster. You're watching Earth from space, 4.4 billion years ago, and something impossible is about to happen. Earth is young, barely 100 million years old, still cooling from its formation. The surface is mostly solid now, with a thin crust covering the molten interior. Volcanoes are everywhere. The atmosphere is thick and toxic, but it's stable. It's a planet. And then, from the darkness of space, something appears. It's another planet, smaller than Earth, about the size of Mars, but still massive. It's called Theia, though of course no one has named it yet. It's been orbiting the sun in a similar path to Earth, and over millions of years, gravitational interactions have brought the two closer together. Now, their orbits have intersected. Theia is moving at about 25,000 miles per hour. Earth has no time to react. no way to avoid it. The collision is inevitable. You watch, suspended in space, as the two planets meet. The impact is beyond comprehension. Theia hits Earth at an angle, not head-on. The collision releases more energy than 1 billion nuclear weapons. The side of Earth that's hit simply vaporizes. Rock turns to gas instantly. The shock wave travels through the entire planet, triggering earthquakes, volcanic eruptions, chaos. Theia is destroyed. Its core merges with Earth's, sinking toward the center, adding iron and mass. But huge amounts of material from both planets are ejected into space. A cloud of vaporized rock surrounds Earth, glowing white-hot. Some of it escapes into space. Some of it falls back to the surface. But a significant amount remains in orbit, held by Earth's gravity. Over the next few thousand years, this orbiting debris begins to cool and condense. Droplets of molten rock collide and stick together. Larger clumps attract smaller ones. Gravity pulls the material into a sphere. The moon forms. At first, it's much closer to Earth than it is now, maybe 15,000 miles away instead of 240,000. It appears enormous in the sky, dozens of times larger than you're used to. And it's hot, still glowing from the heat of formation. The tides it creates are monstrous. Water surges hundreds of feet up and down the coastlines. The moon's gravity pulls on Earth's crust, causing tidal heating, more volcanic activity. But over millions of years, things settle. The moon cools, its surface solidifies. Craters form from impacts. It drifts slowly away from Earth, about 1.5 inches per year, a process that continues even today. And it stabilizes Earth's rotation. Without the moon, Earth's axial tilt would wobble chaotically over time. The tilt is what gives us seasons, summer and winter, predictable climate patterns. But without the moon's gravitational influence, that tilt would vary wildly. Sometimes Earth might be tilted 0 degrees with no seasons at all. Sometimes it might be tilted 85 degrees with extreme seasonal variation. Life would struggle to adapt to such chaos. But with the moon, Earth's tilt stays relatively constant, around 23.5 degrees, wobbling only slightly over tens of thousands of years. This stability allows for predictable climates, which allows for stable ecosystems, which allows for complex life. You exist because Earth got hit by another planet. It's a strange thought. One of the most catastrophic events in Earth's history, an impact that melted the surface, vaporized oceans, nearly destroyed the planet, turned out to be essential for life. It's a bit like a car accident that somehow results in you winning the lottery. Except the car is a planet. The accident is a collision with another planet. And the lottery is the ability to support life. You watch the newly formed moon orbit Earth slowly drifting away, and you think about contingency. So much of existence depends on accidents. If Theia had hit Earth at a slightly different angle or at a different speed, the outcome might have been completely different. Maybe no moon would have formed. Maybe Earth would have been destroyed entirely. Maybe the debris would have formed multiple small moons instead of one large one. Any of those outcomes would have resulted in a planet where you don't exist. But Theia hit at just the right angle, at just the right speed, and the moon formed, and Earth stabilized, and billions of years later, here you are. Existence is fragile. It depends on a chain of improbable events stretching back billions of years, and every single link in that chain had to happen exactly as it did, or you wouldn't be here. And slowly, we drift further back. 4.6 billion years ago, a cloud of hydrogen collapsed under its own gravity until the core became hot and dense enough to begin fusing atoms. The sun turned on. It has been burning steadily ever since, converting 4 million tons of mass into energy every second. It will continue doing so for another 5 billion years. You exist inside its warmth, briefly. You're floating in space, 4.6 billion years ago, in a region that will one day be called the solar system. But right now, there's no sun, no planets, no light, just a cloud. It's enormous, several light years across, a diffuse collection of hydrogen, helium, and trace amounts of heavier elements left over from previous generations of stars. It's called a molecular cloud, and it's cold, dark, drifting through the galaxy. Most of it will remain a cloud forever, but a small part of it, a region about the size of the future solar system, is starting to collapse. Maybe a nearby supernova sent a shockwave through the cloud, compressing it. Maybe it was just random density fluctuations. Either way, gravity takes over. The cloud begins to fall inward, slowly at first, then faster. As it collapses, it heats up. The center becomes denser, hotter. The cloud starts to spin, flattening into a disk with a dense core at the center. This core is the proto-sun. You watch as it continues to collapse. The temperature rises, 1,000 degrees, 10,000 degrees, 100,000 degrees. The pressure increases. Atoms are stripped of their electrons, becoming a plasma, a soup of nuclei and free electrons. And then, when the core reaches about 10 million degrees, something extraordinary happens. Hydrogen nuclei begin to fuse. 2 hydrogen nuclei collide with enough force to overcome their electromagnetic repulsion. They stick together, forming helium. In the process, a tiny amount of mass is converted into energy, according to Einstein's equation, E enrund mc2. That tiny amount of mass releases an enormous amount of energy, and suddenly the sun turns on. Light floods outward from the core. The pressure from the fusion reactions pushes back against gravity, stopping the collapse. The sun reaches equilibrium, gravity pulling inward, fusion pressure pushing outward. It will remain in this balance for the next 10 billion years. You watch the newborn sun shine for the first time. It's smaller than it will be later, still surrounded by the disk of gas and dust that will eventually form the planets. But it's stable. It's a star, and it's burning hydrogen at a rate of 600 million tons per second. Every second, the sun converts 4 million tons of mass into energy. That energy radiates outward as light, warming the planets, driving weather, enabling photosynthesis, making life possible. The sun is not eternal. It's consuming its fuel. Eventually, in about 5 billion years, it will run out of hydrogen in its core. It will begin fusing helium, expanding into a red giant, swallowing Mercury, Venus, possibly Earth. Then it will shed its outer layers, leaving behind a white dwarf, a dense, Earth-sized ember that will slowly cool over trillions of years. But that's far in the future. Right now, the sun is young, stable, and will remain so for billions of years. Long enough for planets to form, long enough for life to emerge, long enough for you to exist. You float in the light of the newborn sun, feeling its warmth even across the vacuum of space. And you think about what it means to live inside a star's glow. Everything you know depends on the sun. Your food comes from plants that use sunlight for energy. Your warmth comes from sunlight absorbed by the earth. Your weather, your seasons, your days and nights, all driven by the sun. Ancient cultures worshipped the sun as a god, and they weren't entirely wrong. It's not conscious, not alive, but it is the source of almost everything. Without the sun, Earth would be a frozen, lifeless rock drifting through space. With the sun, Earth is warm, dynamic, alive. You exist in the narrow habitable zone around a stable, middle-aged star. If you were closer, you'd boil. If you were farther, you'd freeze. If the sun were larger, it would burn too fast and die before life could evolve. If it were smaller, the habitable zone would be so close that tidal forces would lock planets in place, making them uninhabitable. But the sun is just right. It's a cosmic Goldilocks situation, and you're living in it. You watch the young sun burn, converting mass into light, and you realize this process has been happening for 4.6 billion years. Every sunrise you've ever seen, every sunset, every warm summer day, every ray of light that's ever touched your skin, all of it comes from hydrogen atoms fusing in the core of the sun. The light you see left the sun about 8 minutes ago. It traveled 93 million miles through space, through Earth's atmosphere, to reach your eyes. And the energy that created that light came from fusion reactions happening deep inside the sun, where no light can escape directly, where photons bounce around for thousands of years before finally reaching the surface. You are basking in ancient energy, released by processes you can barely comprehend, from a star that will outlive you by billions of years. And slowly, we drift further back. Before there was a sun, there was a nebula, a cloud of gas and dust light years across, drifting through space. Something triggered its collapse. Maybe a nearby supernova, maybe just gravity's patient pull. Either way, that cloud became our solar system. Everything you've ever touched was once part of that diffuse, invisible fog. You're drifting through the Milky Way galaxy 4.6 billion years ago, in a region about 26,000 light years from the galactic center. Around you, space is not empty. There's a massive cloud here, a molecular cloud made mostly of hydrogen and helium with traces of heavier elements: carbon, nitrogen, oxygen, silicon, iron. All of it left over from previous generations of stars that lived, died, and exploded, scattering their enriched material across the galaxy. The cloud is dark, cold, nearly invisible except where it blocks the light of stars behind it. It's several light years across, containing enough material to make thousands of stars, and it's about to collapse. You watch as a shock wave passes through the cloud, maybe from a nearby supernova, maybe from the spiral arm of the galaxy compressing the material. The shock wave creates density fluctuations, regions where the gas is slightly more compressed. And in those regions, gravity begins to win. The gas starts to fall inward, slowly at first, over thousands of years, then faster. The collapse accelerates. The cloud fragments into smaller clumps, each one collapsing independently. One of those clumps will become the sun. The others will become nearby stars, siblings, born from the same cloud, now scattered across the galaxy. You focus on the clump that will become the solar system. It's collapsing, spinning, flattening into a disk. The center becomes denser, hotter. The outer regions spread out, forming a rotating disk of gas and dust around the proto-sun. Within that disk, planets will form. But first, the sun has to ignite. You've already watched that happen. The core reaches fusion temperature. The sun turns on. Light and heat flood the system. And now, in the disk around the sun, something new begins. Dust grains start sticking together. Pebbles form. Boulders, planetesimals, planets. It's the same process you watched before, but now you see it in context. The solar system is not unique. It formed like countless other star systems from the collapse of a molecular cloud through well-understood physical processes. There's nothing special about it except that it's yours. You watch the disk evolve. The inner regions, close to the sun, are hot. Only materials with high melting points can condense there, metals and silicates. These become the rocky planets: Mercury, Venus, Earth, Mars. The outer regions beyond the frost line are cold enough for ices to condense: water ice, methane ice, ammonia ice. These ices, combined with rock and metal, form the cores of the gas giants: Jupiter, Saturn, Uranus, Neptune. It takes tens of millions of years for the planets to form. During that time, the system is chaotic. Planets migrate inward and outward, their gravitational interactions rearranging the architecture of the system. Jupiter may have moved inward, then back outward, scattering smaller bodies and possibly preventing a planet from forming in the asteroid belt. Eventually, things settle. The planets find stable orbits. The leftover material, asteroids, comets, is either ejected from the system or relegated to distant, stable regions like the Kuiper Belt and the Oort cloud. The solar system, as you know it, has formed. You float above the newborn Earth, watching it cool, watching the moon form, watching the bombardment gradually decrease, and you think about origins. Everything you've ever touched came from this cloud. The ground beneath your feet, the water you drink, the air you breathe, the food you eat, your body, your cells, your DNA. All of it was once part of a cold, dark, diffuse cloud drifting through space. Gravity pulled it together. Fusion lit it up. Chemistry made it complex. Evolution made it aware. And here you are, a temporary arrangement of atoms, borrowing them briefly before returning them to the universe. You are made of star stuff, as Carl Sagan famously said. But more than that, you are made of cloud stuff, nebula stuff, the remnants of ancient stars, mixed and recycled, collapsed and reformed, billions of years in the making. You are the universe looking at itself, and slowly we drift further back still.